In the homework question, to go with the thin ring, you're asked to find a few things. What is the electric field at the center of the ring? Where is the field the maximum? What is the maximum field? And what is the field when we get very far away from the ring? Okay, let's start on part A. What is the field at the center of the ring? That part's actually pretty easy. Let's start with the equation for the electric field due to the ring. So part A, E of x is equal to k times x times q over a squared plus x squared to the 3 over 2 I hat. So that's the electric field as a function of x. At the center, that means x equals 0. So then we plug in 0 here. So we get k times 0 times q over a squared plus 0 squared to the 3 over 2 I hat gives us 0. The electric field at the center of the ring is 0, and that makes total sense because every little piece of field from each little piece of charge is going to cancel out. So if we think about this little dq here, that would make a dE that points down. This little dq here would make a dE that points up. And that would be true the same at any 2 points on the ring. So for every point on this side of the ring, there's a point on that side of the ring that cancels it. So that makes sense symmetrically that it's 0 at the center. Where is the field a maximum? Okay, so we'll use our calculus here to find where our field is a maximum. What we know about maxima and minima is that we get a maximum if the slope is equal to 0, or the derivative. So for a maximum, dE dx equals 0. So we want to take the derivative of our expression for E. We don't need to complete it as a vector. It's enough to show that the magnitude goes to 0. So d by dx of kxq over a squared plus x squared to the 3 over 2. We're going to take the derivative of this function. First thing we can do is take k and q outside because they're constants. If we're going to do this derivative, we can do our chain rule here. So I think of this in terms of kq d by dx of x times a squared plus x squared to the minus 3 over 2. The reason I do it this way is because when you do derivatives, you have the product rule and the quotient rule. I can't remember the quotient rule, but I do remember the product rule. So if something is in a denominator, you can write it in the numerator if the exponent is negative. So these two expressions are equivalent. This is a multiplication. I remember the multiplication rule, so I'm going to go for that one. So as I do my derivative here, k and q come outside. And when we do this, we do the derivative of the first term. That's 1 times the second term. Plus the first term times the derivative of the second term. The derivative of the second term we get by doing our power law. So we bring our exponent down, minus 3 over 2. Multiply by the expression in the brackets. The exponent on the thing in the brackets, that has to be reduced by 1. So minus 3 over 2 minus 1 gives us minus 5 over 2. Then you finish your chain rule by multiplying by the derivative of whatever is inside the brackets. The derivative of a squared plus x squared is 2x. Okay, close up my brackets there. Let's see if I can simplify this just a tiny bit. So I've got my kq outside. For my first term here, this is 1 over a squared plus x squared to the 3 over 2. I've got it back in the denominator again. Then here, this 2 cancels with this 2. I've got 3 minus 3 times x, 3x squared. So that's everything in the numerator. In my denominator, I've got a squared plus x squared to the 5 over 2. I'd like to get my exponents the same on the bottom, so I'm going to multiply top and bottom of this side by a squared plus x squared. Gives me a squared plus x squared on the top. A squared plus x squared is the same as a squared plus x squared to the 2 over 2. So when I multiply it on the bottom, I add up the exponents. That gives me a squared plus x squared to the 5 over 2 minus 3x squared. What I'm going for here is a common denominator, so I can add up the fractions. So now I have a common denominator. So I've got a squared plus x squared minus 3x squared all over a squared plus x squared to the 5 over 2. One last simplification step. This is the same as x squared minus 2x. Okay, so this is my derivative. This is dE by dx. For a maximum, I know this is going to equal 0. So let's start to solve this for x, because we're trying to find out where is the field of maximum. So I'll take this equation, divide both sides by kq, so a squared minus 2x squared over a squared plus x squared to the 5 over 2 equals 0. I'll multiply this term up to the other side. So a squared minus 2x squared equals 0. So when I multiply this up, I get 0. So that tells me that a is equal to 2x squared, or x is equal to a over root 2. This would happen the same on both sides, of course, so x is plus or minus this. And then our other choice, where e would be an extreme, would be at x equals infinity, but that's kind of a boring spot. It would be at a minimum there. It would be at 0. Okay, so my electric field is a maximum at plus or minus a over 2, because this is where the derivative of my electric field with respect to x is 0. Okay, there's part B done, or most of B. The other part of B is what is the maximum field. To find that, I'll plug this value of x into our equation for x. So our value of x goes into our equation for x, and we'll find out what that maximum field is. So E of x, let's just write down that equation again. E of x is equal to k times x times q, for a squared plus x squared to the 3 over 2 I hat. So E at x equals a over root 2 equals k times a over root 2 times q over a squared plus x squared. So x squared will be a over root 2 all squared. That'll give us a squared over 2. That's to the power of 3 over 2 in the x direction. And where do we go from here? Down on the bottom, we've got a squared plus a squared over 2. That gives us 3 over 2a squared. And let's see. Let's just come down onto the next line. So I've got k times a over root 2 times q times I hat. Then I'm going to multiply my 3 over 2 exponent in here. So 3 to the 3 over 2 times a squared to the 3 over 2 over 2 to the 3 over 2. Okay, if you need to brush up on your exponents a little bit, 3 to the 3 over 2 is equal to 3 cubed square root. So the 3 is in here. The square root, the 1/2, is right here. So that's the square root of 27. And for 2 cubed over 2, it's equal to the square root of 2 cubed, which is equal to the square root of 2 times 2 times 2 is square root of 8. You can either leave it as root 8 or call that 2 root 2. Either of those two is fine. And then, of course, my a squared to the 3 over 2, you multiply those exponents, it leaves you with a cubed. So let's write down our final answer. So now my electric field at a over root 2 is equal to KAQ over root 2 times root 27 times a cubed over 2 root 2. Okay, one last step to go. Simplify just a tiny bit more. KAQ. That root 2 and that root 2 cancels. This 2 comes up to the numerator. Got an a on top, a on the bottom, so we're left with an a squared. So that is the maximum field of the electric field. So the electric field is the biggest when we're at a distance of a over root 2 away. And then the value of the field is this size right here. So it goes from 0 at the center, builds to some highest point, and then drops off as we get far away. You know, it wouldn't be uncommon to be asked for a sketch of the electric field as a function of x. So it would start at 0, it would go up, and then it would start to fall off. You know, more or less like this, and that would be at a over root 2. E is a function of x. Okay, last part. What is the field if x is much bigger than a? So in this case, E of x is equal to kxq over a squared plus x squared to the 3 over 2 I hat. If x is much bigger than a, then x squared is much bigger than a squared, and x squared plus a squared is about equal to x squared. Okay, so if my x is really, really big compared to a, then the a down here on the bottom doesn't matter, and we can just go with the x squared. So then that's about equal to kxq over x squared to the 3 over 2, which is equal to kxq over x cubed equal to kq over x squared. So if our distance is way further away than the radius of the ring, it acts like a point charge. Which makes sense because we do have a spherical symmetry there. Okay, there's your homework problem all worked out for you.